to recording. Okay, so people playing some weird form of shuffleboard where they're using this elastic cord to generate more energy, aka cheating, as we would say over here. So they have an elastic cord which they use to impart more energy onto the pucks, right? So you're told that when this cord is directly stretched between the points A and B, so when it's straight over here, right? You know that the tension is equal to 20 newtons, right? You're told that the weight of the puck is 425 grams and it's placed perfectly in the center, and you pull it back a distance of 400 millimeters, right? And you know that to pull it back a force of 400 millimeters, you require this force of 100 newtons, right, to hold it at this particular location. So, you know, you also have friction, right? So when you do your conservation of energy in this problem, you'll have to account for that. So there's going to be friction that comes into play. So due to this friction, it's not going to travel endlessly, but it's going to come to a stop after a certain amount of time, right? Okay, so what we're asked to do is that for all of these conditions, when you pull it back 400 millimeters, 100 Newton force, perfectly in the center, with this coefficient of friction, find out how far along the puck will travel. All right, so we don't need to worry about gravity because everything is on the same plane, right? This is a top view of a table that you're getting. So we don't need to worry about gravity. All right, so let's write out the stuff that's known. So what we know is that the coefficient due to friction is 0.3, and that your mass is equal to 0.425 kilograms. And we also know that when you have the unstretched force, right? So let's say that let's call that the force at A, C, B, like that. You know that the force in the string, in this cord, is equal to 20 newtons. All right, so let's take a look at the different positions which this puck will go through. That'll help us to figure out what we need to do to solve the problem, right? So you have this position itself, right? So you have right? So let's say that this is position number 1. Then you have the position where the puck is still in touch with the elastic cord, but when it's perfectly straight, right? So let's say that this is position number 2, right? So what we can do is we can better describe this force as well. We can say that this force is at position number 2, like that, right? And then you have the final position of the puck where it comes to a stop, right? So that is this position here. So let's say that is equal to position number 3, like that. All right, let's delineate these positions because we know them as well. So let's just say that from getting to position 1 to position 2, the horizontal distance is x1. And then from getting from position, which we know, right? This position, we know that this is equal to 400 millimeters, right? And then from getting from position 2 to position 3, where it comes to a stop, let's say that that is equal to this distance d, like that. All right. So in order to solve this problem, we can do the conservation of energy, right? But if you're hard and fast about it, bring the physics into the picture, they'll be like, no, energy is not conserved, there's friction. But if you account for that, a frictional force, that gets taken out of the picture, right? So what we can say is that between position 1, we don't even need to worry about position 2. I mean, we do, but not from an energy perspective, right? So what we can say is that from the conservation of energy, right? We can say that the kinetic energy at position 1 plus the potential energy at position 1 plus the work that your friction is going to be doing from moving to position 1 to position 3. So remember when I told you guys that you have to account for the frictional force being removed from your initial energy? That's why I'm just putting it as a non-conservative force like this on the left-hand side. You can put it on the right-hand side, make it positive, and do things like that. But this is just how I'm choosing to do the problem. I will not take any points off it if you take it on the right-hand side and keep it positive. It still means the same thing, right? That this energy is being lost, right? And that is equal to our kinetic energy at position 3 plus the potential energy at position 3. All right. So in this expression over here, at position 1, what's my kinetic energy?
Zero.
Zero, right? Everything's at rest. Nothing's moving. Similarly, what is my kinetic energy at position 3? And remember, you're looking at the whole system, right? It's the puck plus this string. So what's the kinetic energy at position 3?
Also 0.
Also 0. Everything comes to rest. All right. So these are the only 3 things that you need to worry about. All right. So let's take a look at the frictional force first. So this frictional force going from position 1 to position 3, it's non-conservative. We know it's going to be taken out of this initial position, right? Initial energy, right? So that's going to be negative. And then, just because it's path dependent, if you want to be complete about the way that you write things, you have to express it as an integral, right? So it's going from position 0 to its position of x1 plus d like that, minus times mu k, whatever the frictional force is, right? So the frictional force, sorry, I already have the minus outside. The frictional force is equal to mu k times mg, right? Which is the normal force. So mg like that times dx, right? Ultimately, it's a straight line, integral of the straight line. If you just straight away just write it, that's going to be minus mu k mg. So this is your frictional force times x1 plus d like that. No points taken off. This is absolutely fine for writing your friction energy, right? And the reason to have this minus sign is because you're taking it out of this initial energy. So it's lost, all right? So that's why this sign makes sense. All right, do you guys have any question with this term over here? With this frictional term?
Where is the position 0 on your drawing?
Oh, right here. Thanks. That's a good question. Yeah. Position 0 is right here. All right. So basically from 1 to 3. So 0 is position 1. Okay. Then now we need to worry about our potential energy. So potential energy at position 1, we can say is equal to 1/2 times k times whatever the extension is at that position, right? And then we can say that the potential energy at position 3, right? What we're going to assume that at position 3 is that the chord is straight, right? So let's say that here chord is straight. Right, so it's in its straight position when the puck comes to position 3. So it's half, and let's say that that's half times k times S3 squared, right? And in bracket, you can note to yourself that S3 is when chord is straight along, I guess we'd call the points ACB, right? So if you want to write it here, ACB. So along like that. All right, so what we need to do is basically find out what we need to find out k, we need to find out S1, and we need to find out S3, right? And we can do that by looking at these conditions of the geometries. We know what the lengths are, and we know what the forces are, right? So we can find out, if we can find out what the force is in position 1 and find out what the force is in position 2, we can basically find out what your spring constant K is going to be. And then using those expressions, we can find out what your extensions S1 and S3 are going to be. So let's define some more things over here, right? That will help us figure those things out in a more clear manner. So, right, so let's say that the length of the chord in position 1 is L1, right? So that's the length in position, so that's going to be this big length over here. The length of the chord in position 2 is L2, like that, right? And then you have the stretched lengths that you've defined, S1 and S3. So remember here, S1 and S3 are stretched lengths. Okay, so now to find out what your length of the chord in position 1 is, the drawing kind of tells you that you can assume that it becomes perfectly pinched at that point, right? So you can just use geometry to find out what that length is. So if I look at the length, like that, I know this is equal to 300 millimeters. I know that this is equal to 400 millimeters, right? So this is going to be L1, right? It's just going to be 2 times this length squared, right? And that is equal to, convert everything into meters, you get 0.3 squared plus 0.4 squared, and the square root of that, right? And it's 2 times that because you're taking the, you're considering it's twice the length, right? Is that clear, everyone, guys? It's basically just Pythagoras' theorem, right? So from here, you get L1 is equal to 1 meter, like that. All right, next, what we need to do is to find out our spring constant, we actually need to find out what the force is in the spring, in this guy, in the extended condition, and then we already know what it is when it's straight, so we can then use that. But in this extended condition, we need to do a quick equilibrium to find it out, right? So we need to find the force in the chord, right? And we know that in that initial position, it's being held there, so it's kind of like you can say that it's an equilibrium. So if you say that that is my chord, like that, right, you're going to have this tensile force that's acting on it, right? So let's call it F chord in position 1, like that, symmetric F chord in position 1, like that, right? And you have this force, which is pulling it back by 100 newtons, like that, right? And then you know this is 400, 300. If you take a look at it in millimeters, this is 500. Right? So if you do your equilibrium in the x direction, so if you define your coordinate frame y and x, what you see is that you'll have 2 times f c1 times the cosine of this angle, which is just 400 over 500, right? So that's just equal to 4 over 5, right? Minus 100 is equal to 0. If you solve that, your force comes out to be equal to 62.5 newtons.
Where
Right.
did the 2 come from?
There is, there's two, there's two chords, right?
Right.
So that's where the 2 comes from. So you'll have a component for this one, and you'll have a component for this one. So the 2 comes from the fact that it's basically FC1 4/5 for this force plus for that force. Is that clear?
Yes, sir.
Did you say the angle is going to be sine of 4/5?
No, it's going to be cosine of this angle, right? And the cosine of this angle is equal to 400/500, correct? Did I mess that up? No, I didn't mess that
No.
up. That's
No,
correct.
okay.
Yeah.
No, it's correct.
So yeah, I guess you guys can shout at me for skipping steps, but this is cosine theta over here. Okay. So now you found out what your force is in this position in your chord. And that will help you solve for what your spring constant is and for what your extension is, right? So basically, anyways, before we move on to that, any questions? It's pretty straightforward stuff till now, right? Okay. So are you guys, can we move on to the next page?
Where's L1 one more time, please?
L1 is this position of the chord, the total position of the chord when you pull it back. It's L1,
Oh, okay, thank
the
you.
total position. Okay, and L2, you know, is just going to be 300 plus 300 or 0.6 meters. Okay. All right, I'm moving on, guys. So let's introduce another unknown just for our understanding. It's not going to mess things up. Let's say that the undeformed length of the chord is, let's say that that's L0. Right? What I can say is from the things that I've defined that my force in the chord in its initial, in the one position, right, where it's basically pulled back and it's bent like this, right? I know that that force is equal to my spring constant times my extension in the first position, right? And similarly, I can say that, I guess I called it A, C, B, comma 2, right? That force, when your chord is straight, is equal to this times your thing. But this we can say is also equal to the deflection in position 3, because in both the positions, the chord is going to be straight, right? That's the assumption that we're making. So in both position 2 and position 3, the chord is going to be perfectly straight.
Will the chord move past 2 or it will stay straight at 2?
So in a real world condition, it will move past 2. But what we're assuming is that between the puck moving from position 2 to position 3, it moves, but then it comes back into equilibrium and becomes straight. That's the assumption that is necessary for us to make, because otherwise we don't have enough conditions to solve the problem.
Okay, thank you.
But you're right, it'll never be perfectly straight, right? At 2, it'll go back and it'll oscillate a little bit, and then it'll become straight like that. Okay, so now what that means is that I can subtract these two expressions. So subtract, what happens is I get that FC1 minus FACB2 is going to equal K times S1 minus S2 or S3, like that, right? So I know FC1 that we just found out is equal to 62.5 newtons, right? FACB is given in the problem. They told us that it's 20 newtons. So minus 20 newtons like that. This K is an unknown. Now we can find out this difference because we can say that the extension S1 is just equal to L1 minus L0 minus your extension S3, which is just equal to L2 when your chord is straight minus L0 like that, right? From here, what you see that this L0 cancels out and you're left with K times L1 minus L2 like that. And both of these are known, right? So this is just equal to K times L1, which we found to be equal to 1 minus L2, which we know from the problem statement. Where do you go, mouse? To be equal to 600, right? Or 0.6 when you convert things into meters. So that times 0.6, that's in meters like that. So from here, you get K is basically equal to, and guys, I'm writing these down, but I hope someone's confirming these, right? So I got 106.25 newtons per meter, like that. Okay, and now you can find your S1 and S2, right? So now right, so S1 is equal to your chord being extended at position 1 divided by the spring constant there, and S2, which is also equal to the deflection at 3 because we're assuming that the chord remains straight there. That is equal to your force, that's the problem gives you when it has to be straight, divided by K, like that, right? So you get 62.5 newtons divided by 106.25 newtons per meter. This is equal to 20 newtons divided by 106.25 newtons per meter. Right? And what I got is that this is equal to 0.5882 meters. This guy is equal to 0.1882 meters. And that's it. You now have everything that you need to solve this expression over here. So going back to your energy stuff, right? You see that potential energy position 1 plus the work that's done and lost to friction is equal to position potential energy at position 3, right? And now we know all of these values. So that's just 1/2 times K times S1 squared minus mu K mg times x1 plus d is equal to 1/2 times K times S3 squared. And the only unknown here for this expression is D. Everything else is known. So you plug everything in, you get 1/2 times 106. And remember, newtons per meter, keep your units, be careful of your units, right? So everything's in meters. So 0.5882 squared minus 0.3 times, converting the grams into kilograms, so 0.525 kilograms times gravity, which is 9.81. X1, what was X1? 400, so 0.4. So you get 0.4 plus D is equal to 1/2 times 106.25 times S3 is 0.1882 squared, like that, right? One equation, one unknown D. If you do the solving, get that D is equal to 12.79 meters.
Would you have to add in that original length to start to D since we defined D as from 2 to 3?
That's right. That's this X1 is coming in, right? And we added that in 0.4.
Okay.
Absolutely. So you can tell when you write the answer out, be sure to tell everyone that D is measured from this position, from C. All right. The total travel is obviously going to be that plus D, right? So that's a good catch, Mr. Davidson.
Wouldn't that be the answer at the end?
Yeah, so you might want to add that to this, right? So right, did I do that mental math correct? 0.4, yeah, all right. Good catch, good catch.
I've got a quick question. How do
Yeah.
you 106.25 Newton meter spring constant again?
That is from looking at your, we found out what the force is in the cord due to the stretch configuration. And the problem statement tells us what the force is when it's straight, right? So we basically took advantage of that to find out what this K basically was over here by just subtracting these expressions for the two forces.
All right.
Does that make sense?
Yeah, I'll go back and look at it.
It's basically, you need to know what the forces are in the two different positions. And once you have that and you know what the lengths are, you can just subtract the two and take advantage of the fact that, even though it's an extension, right, you can reduce the number of unknowns by just subtracting the two positions, right? Because when you subtract the two deflections, you get rid of the original undeformed term over there.
Yeah, no, I understand the concept. I think I have to just do it out myself to see how it works out to be what it does. So.
Okay. Yeah. Well, I'm trying to see if I can explain it a better way. This one is 3. So there's another way to think about this, right? What you can think about it in another way is you can think of these as being two expressions with two unknowns, right? So this is K times L1 minus L0, and this is equal to K times L2 minus L0, right? So in these expressions, basically F equals that and F equals that. You can think of these being two expressions for two unknowns, K and L0. And there you go. Does that make it better?
I think so.
All right.
I know how to find the spring constant. Like
Yeah.
the angle, like all the angles and the two angles, or I should say the one angle is just throwing me off a bit because I'm used to doing it when like the spring in the end doesn't have any like energy left in it, and in this instance it does. So
That's right. That's right. It's exactly what you said, and you understand it perfectly.
all right, thank you.
Yeah. I guess this is a better way of looking at it. Two expressions for two unknowns, for me at least. So there you go. All right. Any other questions, guys? If not, let's look at the last problem. Oh, were you going to ask a question? Was someone going to ask a question?
Yes. I struggle a lot trying to come up with the procedure for solving questions. Like sometimes I don't know what step do I start with first before
Sure.
moving to the next step. Is there any way you could summarize what we did on this problem and why we did that?
Absolutely. Yeah. So in this problem, first step, we know that we have to use energy conservation, right, to find out how far it moves. We looked at our energy conservation equation again. physicists are going to hate me for saying this is energy conservation because there's friction coming in, but we account for that with the friction term. All right. Then we break down the terms in the energy conservation, right? And we realize that we need to know what the spring constant is for this elastic cord, and we need to know what these two extensions are. All right. Everything else in this expression is given to us in the problem. Now, in order to find the spring constant and the extensions, you have to go back to the question and see that you have the forces and the dimensions for the two different positions. So you can intuitively figure out, all right, with that information, I can figure out what my spring constant is and what my extensions are. And that's basically what this whole process was over here. And once you figure those out, you go back to your energy expression and you just solve that to get what your solution is.
Thank you.
All right, so last problem. This is problem number 5 on the problem set, right? So here, what you have is a 1.5 pound ball that can slide on a horizontal frictionless surface. You have an elastic cord of spring constant K, 1 pound per inch, and it's tied to a point. Initially, as soon as you see that, you can say, all right, this is going to be a conservative force and it's going to centrally act on it because it's fixed at the pointer. So I can use both conservation of energy and my conservation of angular momentum. All right, and you're told that the undeformed length for this cord is equal to 2 feet, right? So basically when it's at 2 feet, it's at its undeformed length. Now, you have this initial condition where the ball is placed 3 feet from the pointer. So it's extended at this position by 1 foot, right? And it's given an initial velocity V0, which is perpendicular to this string or OA initially, right? And the first part of the problem is asking you to find the value of the initial speed V0 if the cord is never to become slack. All right, so basically if the cord never becomes slack. Right? And the second part of the question is asking you to find the closest distance d the ball will come to the point O if you give it half this initial speed that you find in the first part. All right, so let's say that for all intents and purposes, this is position 1, and then the position that we're solving for in both of the problems is position 2, right? So let's just say that this is position 2. It says it's D in this problem, but let's just say that, you know, it's position 2, like that. All right. So what we can do is we can find out, we can use our conservation of energy, and we'll see if we need to use the conservation of angular momentum if we don't have enough unknowns, right? So what we can say is that for part A, you have the initial energy, mechanical energy, right? So that's kinetic energy plus potential energy at position 1. And then you have the potential energy and kinetic energy at position 2. That's the position that we're trying to solve for. Here, position 2 for this problem is basically just when the cord, let's say is, so position 2 is just when the cord, all right, let's just say in general position 2 is just closest point, is closest point of approach to O. All right, and that's the position that we're solving for in both of the problems, so to speak. All right, so for part A of the problem, if we write out what the expression is, right, we know that the initial kinetic energy is going to be that the ball has a mass m, right? So you have the mass m times the initial velocity squared that we're trying to solve for, right? So let's just call that V0, like that, right? Plus half times the k times whatever the extension is, right? So here you have L1, and this is L0, right? So you can say L1 minus L0. Well, this is L1, and L0 is the undeformed length, right? Right, so L1 minus L0 squared, right? So that's equal to my energy of the system when it's in position 1. In position 2, my body will still have energy, right? So that's half m v2 squared plus 1/2 times whatever the length is in position 2 minus the original length, like that, right? So here, the one thing that we can straight off say is that for the point of closest approach, you don't want the cord to become slack, right? So you can say that for position 2, you can say that L2 is going to equal L0, which is going to equal 2 feet for 0 tension in the cord at the closest point of approach, right? So basically, whenever it gets closest to the thing, you don't want it becoming slack, but it can become just a little slack, but it's not really slack. So it's its initial undeformed length, and then it's just going to become longer after that, right? So for 0 tension in the cord at closest the approach. Is that clear to everyone? Why we're making this assumption, right? We're making this assumption because we're saying that the cord is never becoming slack. So if it's never becoming slack, when it comes closest to the point O, it's going to be its original length, right? And then it'll become longer, or it was always longer before that, right? So we know that at its closest point of approach, if the cord is just enough, we're asked to find the minimum velocity, right? So this, we can clearly say that this is true. Is this clear to everyone, guys?
Yeah.
Is it, all right, let me ask the question another way. Is it not clear to anyone? Okay, so if, were you going to say anything? Was someone going
Nah,
to say that?
thank you.
Okay, all right. So in this expression, if you take a look at everything, right? We know what M is, we know what K is, we know what L1 is, we know what L0 is, right? We figured out what L2 and L0 are already for the condition which the problem is telling us. But you have two unknowns, right? You have V0 and V2, right? So what you need is, you need another expression. And where does that expression come from, guys?
Does that come from momentum?
That's right. That comes from angular momentum, right? So we need a second expression. Right? And we can just straight off say, always assuming that even when it reaches its position 2, right, the velocity is going to be perpendicular to that position, right? So what we can say is that we need a second expression, and this comes from conservation of angular momentum. Right? And we can say that L1, the perpendicular distance times m times v0, which is the angular momentum initially, right, is equal to the perpendicular distance it goes in the second position times m times this v2 over there, like that. Right, and from here, you have your second expression, right? So now you have two expressions for two unknowns that you can use to solve the problem, right? So you have to make our life easy, if you don't want to use Mathematica, if you want to do it by hand, you can say from here, that V2 is just equal to L1 V0 over L2, right? And here we know everything. Well, we know L1 and we know L2. V0 we just plug in. So if we plug this in to position 1, so you will find out what your expression for V0 is, right? So what you end up with is plugging in V2 from your equation 2 into expression 1, and you do some amount of playing around with it, right? You get the expression that V0 squared minus L1 squared over L2 squared times V0 squared is equal to minus K over M times L1 minus L0 squared plus like that. All right, guys, we're going to go a little bit over, so apologies for that. I guess that just happens with us all the time now. All right, so you know everything in here. I'll give you guys what it is, but you can solve it for yourselves, right? So we know that L1 is equal to whoops, wrong page. L1 is equal to 3 feet. Right, L0 is equal to 2 feet. L2, we found out from the conditions that the problem is also going to be equal 2 feet. Then we're told that K is equal to 1 pound per inch. So be sure, this is in feet, so you make sure that you convert the inches into feet, right? So that gives you 12 pounds per feet. And then the mass is just equal to, the problem gives you the weight, right? So the problem gives you the weight of the ball is 1.5 pounds. That's just equal to W over G, right? So that's just 1.5 pounds divided by gravity in pound foot per second squared, right? And that's 32.2. So this, whatever you get, whatever quantity you get in pounds per second squared per foot, like that, right? You plug everything in and solve for V0. I'll give you guys the final answer. You get V0 is equal to 14.36 feet per second. And what that's saying is, you'll get plus or minus this if you look at it weirdly enough. But all that means is that, it's the two different directions, right? You're either going forward or backward. So you can just take the positive one over there.
Could you scroll up a little bit to the expression?
Yes, of course. Sorry about that. So here you say, when I said two expressions for two unknowns, the two unknowns are basically V2 and V0, right? Anyone else have any questions? All right, so for the next part of the problem, it's pretty straightforward. You're told that the closest distance d that will come to point O, if it's given half the initial speed found in part A, right? So if we go do that, so for part B of the problem, what you're told with is that V0 is equal to 1/2 times, what do you get here? So 14.36 feet per second. So that comes out to be equal to 7.18 feet per second, like that, right? And you do the exact same thing, but now you know what your V0 is, right? But you don't know what your energy is going to be, right? So for here, now we look at the conservation of energy. Right, again, you have T1 plus V1 is equal to T2 plus V2 like that, right? So we have 1/2 m V0 squared plus half times K times L1 minus L0 squared is equal to 1/2 times m V2 squared, right? What's the potential energy at position 2 going to be for this case where you have half the velocity given to the ball? Right, so you give it half the velocity.
Like the potential energy would be half then.
No, it wouldn't. If you give it half, so the first part of the problem was the smallest amount of the velocity of the ball so that the cord never becomes slack. If you give it half the velocity, what's going to happen to the cord at the point of closest approach?
It's going to have slack.
It's going to have slack. And what does that mean for this cord? Its potential energy?
Is it free fall?
0. It's not under, this is not under gravity. This is not on, you're again on a table. All right, this is again on a table. There's no gravity. You're looking at the top view. Right, so the potential energy is going to be 0 because it's going to be, cord is going to be slack. And unlike a spring, which deforms both ways, when a cord becomes slack, it stores no energy. So cord is slack at point of closest approach. So here's an important note for you guys, that the cords only have energy when elongated, right? So only when they're in tension and when they're pulled, not when they're compressed. Is that clear, guys? Is that not clear to anyone?
It's clear.
Okay, so again, you have one expression, but you have two unknowns, but you can apply your, sorry, what did I say? Control Z. Right, so this will give you what the velocity is going to be at the point of closest approach, right? So you can use this expression to find out what V2 is, right? So one unknown. Now, but the problem is not asking you to find out what V2 is, right? The problem is asking you to find the closest distance D that the ball will come to point O, right? So to find that, you use conservation of angular momentum. Right, and you can use the expression that you have R1 M times V1 is equal to, not R1, sorry, we said L1, right? So L1 times V0 is equal to D M times V2, like that. So here, if you don't want to solve for V2, you can plug it in, right? So basically you get your V2 expression here, plug it in here, and solve for D, right? Because you know everything. You know L1, you know M, well, M cancels out, right? And you know V0, you can find D, right? So D is equal to L1 V0 divided by V2. Again, in Mathematica, you can treat this as two equations with two unknowns if you'd like, but you don't have to. You can solve for V2 from this expression, and then you can just plug it in here to find out what your D is going to be, right? So solve for V2, and you get that that is equal to, I'll just give you guys what I got. If it's different, you guys let me know. And then let's call this is expression 3, expression 4, right? So use 4 to find that your closest point of approach is equal to, ends up being 1.225 feet. So what you've done with this expression on top is you find the velocity of ball at closest approach. All right, guys. Do you have any questions?